Okay, today I want to talk about a really typical calculus problem that's usually introduced right after you're made aware of the fundamental theorem of calculus that has to do with the relationship between a function being integrated and differentiated. And what we're seeing here is that there's a function defined. G is a function. It's a function of x, which means as you plug in values for x, you're going to get quantities out. However, it's written in an interesting way. It's written as a definite integral with limits. However, the upper limit is the variable x. So in other words, if you wanted to find out what g of 5 is, you'd plug a 5 in here for x. And you would take the integral of f of t dt, which in this case, we don't have the function for f of t, but we have a picture of it down here, which is all we're going to need. And you would plug a 5 in here, and you would basically compute the integral, whether it means you're going to do it by hand, using like a power rule or a trig integration or something like that, or you're just going to understand that a definite integral represents an area and be able to compute that area somehow. And that's exactly how these problems are going to get done. We're going to recognize that if we're talking about the area bounded by f of t and the t-axis, it's going to be pretty easy to compute because it's divided into these little triangles and things, and sometimes you'll see semicircles, straight line segments. It's usually a combination of semicircles and straight line segments, so you can break it up into very identifiable regular geometric areas. Anyway, so g is a function of x, and the way you get the values is you compute the area, which is what's represented by this symbol. This definite integral represents the area bounded by f of t and the t-axis here. Between this number and this number, between 0 and x in this case. So x will be sort of like, you could think of it as like a random value along this t-axis. The t, the fact that it's that's the independent variable here, you could sort of think of that as being anything. It's kind of arbitrary. It could be t, it could be r, it could be q, anything except x, because x is going to wind up getting dropped in there. So if you combine to that, the first thing it's asking us is write a sentence explaining what's meant by the expression g of 2 in the context of this problem. Well, g of 2, you think about putting a 2 there, which means you'd put a 2 here. So it would be the integral of f of t dt from 0 to 2. You think, okay, well, I know what that means. That means get me the area bounded by f of t between 0 and 2. So you'd say, okay, going from 0 to 2 on the axis here, how much area is bounded by our curve? So it would represent this area right down there. And maybe I can highlight that, and we'll see what we have here. So if I was going to fill that area in, it looks like that is a triangle. And the area of a triangle is 1/2 the base, which is 2 units, and the height of that triangle, which looks like it goes down to -2, so that's 2 units. So that value is 1/2 of 2 times 2, which is 2. Now, we would consider that area, because it's below the x-axis, we would consider it negative. You could think of maybe that this 2 right here being a -2 because it goes down 2 units. But anyway, so that's what would be represented. That's what the term g of 2 would represent, the area bounded by the function f of t and the horizontal axis between the values 0 and 2. So I'm not going to write all that out because you don't want to sit here and watch me write that, but that would be a nice sentence to describe g of 2. Now, we're going to just proceed in that manner to determine all of these values, and basically we're just going to be doing a bunch of addition and subtraction of areas, whether they're above the horizontal axis or below. But first, the question we're asked is, what's g of 0? And you think, okay, g of 0, that means we're putting a 0 in there, which means we're gathering area from 0 to 0. It means we're sitting right here, we didn't move anywhere. So we're not going to gather any area, so that's just going to be 0. We've already computed that g of 2 is -2. And then when we get to g of 4 here, we're going to pick up another congruent, or triangle that's congruent to that first one. So that area is also going to be another -2, so that by that time, we've now accumulated this whole batch of stuff here that's underneath the axis, and that now would be a net total of -4 square units of area. Now, when we get to g of 5, we're going up above the x-axis, or the horizontal axis, I should say, because it's technically it's the t-axis. So what we've got now is that little bit of a triangle that looks like it has a base of 1 and a height of 2. So that's going to be 1 square unit inside there, and it's positive. So to get g of 5, we're going to think of the negative 4 units that we had before, but now we're adding 1 positive unit, so our net is going to be negative 3 there. And we're just going to proceed a little bit further over to pick up at g of 6 what we have here. And it looks like g of 6 has these 2 units at the bottom, and then it has a triangle that's 1 wide and 2 tall. So that's another 1 unit there. So it looks like that's going to be an additional 3 units of area. So we would have the negative 3 that we had at 5, and then we're picking up 3 more positive. So now we have a net area of 0. Basically what that means is that this green area here is equal but an opposite sign of the blue area that's below the horizontal axis. So by the time we've gotten to g of 6, or by the time we've gotten to x equals 6, we now have a net signed area of 0. We can proceed now to g of 8, where we're going to pick up this triangle's worth of stuff, which looks like it's 2 wide and 4 tall. 1/2 of 2 times 4 is going to be 4, so we're going to pick up 4 units of area, and that's going to give us a net total of 4 now. And now we've gone all the way out to 8, so all that area accounted for. And now g of 10, we're going to lose a little bit of area because we're now going down below the x-axis for a triangle that is 2 wide and 2 deep. So we're going to go 1/2 of 2 times negative 2 again, and that's going to be negative 2. So we're going to lose 2 units in this last little bit of stuff underneath the horizontal axis. So we were at 4 units, we're going to lose 2 and go down to 2 units. So there you go. It's basically, a 6th, 7th grade geometry student can do this stuff with basically the area of a triangle, just understanding how it works. If it's above the horizontal axis, it counts as positive, and if it's below, it counts as negative. That does assume that we're moving, to the right across the horizontal axis. We will occasionally see some problems later on where we might have a situation where we might, let's say we have a semicircle here, and this is 4. So if the function were defined as, g of x, we're starting from 0 and going to x of f of t, and they were asking about g of negative 4. I should have a negative there, of course. That would be the area from 0 to negative 4 of f of t dt. And that means we'd be, you could think of it 2 ways. You could think of it as starting here at 0 and moving backwards and gathering up area backwards. And I've talked about that before, where when you're going backwards above the x-axis, it counts as negative area. Or you could use one of the properties that we have for integrals, where we could say this is the opposite of going from negative 4 to 0 of f of t dt. That when you switch the limits, when you switch the order of the limits, you can compensate for that with a negative sign. So you just think of, okay, we're going to go from negative 4 to 0, but choose the opposite value. I just kind of think of it in terms of where you're starting from at 0, going backwards. It kind of makes sense that the area would sort of count backwards. So that's something we don't see it in this problem, but we could in others. So moving along now, for what values is g is increasing? So you think about when we first learned about increasing and decreasing functions way back, we just said, okay, a function's increasing if its derivative is greater than 0, positive. It means it has a positive slope. So I'll write positive slope. Okay, well, we would just need g prime to be positive. Well, if you think of it, g is kind of represented as the antiderivative of f, so g prime would get us back to f. That should kind of make sense. If you integrate f to get to g, if you take the derivative of g, you should get back to f. So, gee, if we only had some information on g prime, well, we do. It's f. So all we have to think about for g prime to be greater than 0 is for f to be greater than 0. So f, we have a picture of it right here, and you think, okay, where is this function positive? Well, you could ask an Algebra 1 student, where is a function positive? And they're going to say when it's above the horizontal axis. So it looks like g prime, which is the values of f, the y values of f is positive between 4 and 8. So we would just have to write on the interval from 4 to 8. Generally, we always write open intervals here with parentheses rather than brackets. Similar reasoning. When is g decreasing? In this next question, well, of course, that's going to be when f has negative values, which is below the x-axis. So we will go, say, from 0 to 4. Make that look a little bit better there, 0 to 4. And then again from 8 to 10. So this information is going to come in real handy for all these things. Now, if you think about having an absolute max, back in the day, we said, okay, absolute maxes occur at critical numbers, which is where the slope goes from positive to negative, maybe the slope's undefined, or where you have your endpoints. Because remember, you could always be talking about a function that might have values like this that start here and they go up and they come down and then they go up and then our interval ends. And although nothing particular is happening interesting there calculus-wise, there's nothing happening with the slope there that's interesting. The slope is 0 here and the slope is 0 here. But this turns out to be our absolute max just because it happened to be where we ended when we were on an upward run. So to think about an absolute max or an absolute min, we would just think about, okay, when does the derivative of g change signs? So basically, and we're going to find max is when it changes from positive to negative. So this derivative of g, which again is f, looks like it changes signs from positive to negative right here at 8. And as you go through these numbers, 0, -2, we're losing values. Once we start getting above the x-axis, we start to gather this positive green material. By the time we get to 6, we're at 0. Then by the time we get to 8, we've gathered up all this positive, numbers, value. And at 8, we've gotten a whole bunch of positive stuff, and then we start losing stuff again. So it makes sense that right here at 8, that's going to be our max. Now, we'd want to check that with our endpoints, but clearly it's bigger than 0, and it's bigger than 10, the value of 10, which is 2. So there's our absolute max. So for what value of x does g achieve its absolute max? That is x equals 8. And what is the absolute max value of g? Well, it is 4, because that's the y value there. And as far as getting an absolute min, you want to think, okay, it's when our slope goes from negative to positive, or at an endpoint. We have a slope going from negative to positive. The slope of g, which is the value of f, goes from negative here to positive there at 4. And as you can check our numbers, we bottomed out at -4 before we started to make our way back up to -3, and then 0, and then 4, and then back down to 2. So that makes sense with our numbers. Of course, you check the endpoints. It's smaller than our endpoint on either end. So I think we're fairly safe in saying g gets its absolute min at x equals 4. And that value, of course, that we found up there in part D is -4. Now, for the last section here, part O, all we have to do is create a graph of g, and that might seem really daunting, except for the fact that we have a whole slew of points that we can graph. We can just plot those points and start to get a picture of it, and it should make some sense. So I'm just going to go plot the points that we have. At 0, we have 0. At 2, we have -2. At 4, we have -4. At 5, we have -3. At 6, we're back to 0. At 8, we're up to 4. And at 10, we're back down to 2. So we're going to have a curve that just basically connects those dots. We could get, a little interesting here and say, all right, the only thing we haven't really talked about is when g might have an inflection point. That'd be kind of cool because we could get the nature of our curvature in here. And we could say g has an inflection point when g double prime changes sign. And you're like, well, that'd be great if I had g double prime. I don't. Well, wait, maybe we do. Because if you think of this relationship over here, that g prime is f, so g double prime, in other words, take the derivative of that guy, you're going to take the derivative of this guy, you're going to get f prime, and f prime is the slope of f. Well, I can see f. It's right here in front of me, so I can certainly see where f's slope changes sign. F has a negative slope, then it has a positive slope. So G double prime would change signs at x equals 2. So that's one place, x equals 2. And it looks like it has a positive slope all the way up to 6 at x equals 6, and then it changes sign and has a negative slope again. So it looks like 6 is a place where G double prime would change signs because the slope of f changes signs. And then lastly, again, right here at 9, because the slope goes from negative prior to that, the slope of f goes from negative to positive. So again, we're talking about G double prime being f prime, which is the slope of f. So if G double prime is changing sign, that's because f prime is changing sign, which means the slope of f is changing sign. So I'll add 9 to my list, and those are going to be inflection points. So let's see, at 2, so this thing is coming down, and of course we have a negative slope of f. So f prime is negative, that means G double prime is negative. So that means we're concave down there. So we're going to be concave down. And then it has f has a positive slope basically from 2 to 6. So that's going to be concave up. So I'm just going to kind of do a little bowl shape thing there. This is not going to be perfect actually, but you'll get the picture. Then we have negative slopes in f, which means f prime is negative, which means G double prime is negative, from 6 to 9. So we're going to be concave down. Okay, so I just kind of left ourselves off there at 9. Then we have another inflection point at 9, so I'm going to make this last little bit of the curve from 9 to 10 be concave up, sort of. So there you go. That's a pretty, I think, doable type of problem. These are really common for one of the 6 free responses on the AP/AB exam. You'll most likely have one of these problems. So we want to get real used to doing it. We want to get real comfortable with it. So you go in there and you could knock out all 9 points, put those in the bank, and wind up doing well in the AP exam. So plenty of practice for this out there.